I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks. I'm a professor of material science and engineering at the University of Utah, and I'm joined by Andrew Falkowski. Andrew, how are you?
A little tired. It's an early morning, but it's good to be here. I think this is an exciting episode, and can't wait to get into it.
Yeah, it's early morning for us because we are joined by somebody in, is it the Netherlands?
Correct.
Yeah, we are joined by Aaike. Aaike, give us a brief introduction on who you are and what your company is.
So, hi, thanks for having us on the podcast. I really enjoy listening to the podcast, and I've listened, I think, most of the previous episodes. So, for those that don't know me, my name is Aaike van Vugt. I graduated almost 10 years ago from the Delft University of Technology as a chemical engineer. And in my last years, I co-founded the company VSParticle. And VSParticle, we started off as being the nanoparticle company, and now we are shifting into becoming the nanoporous layer company. And I'm really looking forward to tell you more about our fundamental technology and how that can be applied to very important applications.
Perfect. Actually, we've had another episode where somebody else during their grad program invented a technology and saw it all the way through to commercialization. And you'd think that these were common by listening to these episodes, but this is incredibly rare. Most students don't get this happening. So I think that's awesome that all the way from grad school to now commercialization. What's that been like?
It has been a very, very educational ride. So people say that you need to do an MBA or you need to do these kind of things. But I think what I've learned by really trying to build a commercial organization in the material space in the last 10 years is by itself the most valuable thing that I gave myself in the past 10 years. In respectful of the financial success that maybe VSP will bring, I think the experience is one of the best.
Rad. Well, I met you at the Accelerate Consortium meeting, right? The Acceleration Consortium has this conference called the Accelerate 2024 or whatever it was this year. And I saw your check and I was like, dang, that is really cool. And you've got some really cool partners. And so we thought, maybe we talk about this technique because it's not one that I had heard of before. The technique that you invented during your PhD program and that you've now commercialized through VSParticle is known as spark ablation. And I'm guessing most of our listeners have never heard of it before. So maybe let's set the stage and tell people what on earth is spark ablation. Maybe you tell us about what the discovery looked like.
Yeah, I need to say that it's not really my discovery. So I came in contact to the technology at the right time. And then the Professor Andreas Schmidtwald, who was back then still a professor at the University of Delft, has been working his whole career on spark ablation technology, starting back from the 80s. And he asked me the question if I would be interested to do more with the technology than just using it in his group. And that was the start of the company. But let me bring you back to the beginning of spark ablation.
Perfect.
So back in the 80s, there were no advanced microscopes that could help us seeing very small nanoparticles. But still, people were aware about the fact that nanoparticles, which is basically an inorganic particle in our case, you also have them in the organic space, but in our case, inorganic, I would say between 1 and 10 nanometer in size. I think in some sense, nano refers to anything between 1 and 100 nanometers, but to be honest, I think they should have been that smaller. It's between 1 and 10. Beyond 10 nanometer, it's more towards bulk properties. So the big shift in physical properties is between, let's say, 1 and 5 nanometer. So back in the 80s, people knew that nanoparticles existed, but nobody knew how to make them. You don't have tweezers to pick up a nanoparticle and put them into your battery, or to pick up a nanoparticle and put them on top of your solar cell. So it was really the early days. So people were asking themselves, how can we make them in an effective way? And then Professor Andreas Schmidtwald started his PhD with the technology that they took a metal wire, a thin metal wire, and they put so much energy into it that the wire would just explode. And out of this explosion, you get the formation of all kinds of fragments, big fragments, but also nano fragments. And he was working in a research group that was good in aerosol measurement. So they could measure inorganic small fragments floating in the gas, basically. So he has a system that could detect nano fragments in the gas downstream after this wire was exploding. And that gave him the capability to understand how these nanoparticles were growing at these explosions. But then by accident, which is how most innovations are discovered, his wire was broken. And instead of this big bang, he got these very small sparks going between the two ends of the broken wire. And then his setup was still up and running. So he could still see that nano fragments were coming off of his sparking wires. And he thought this is a much more elegant way to make those nano fragments compared to exploding the complete wire, where you get all kinds of chunks at the same time. So that was back in the 80s. He was helping one of the first patents on spark ablation. And then his whole scientific career, he kept on asking himself the question, are there other methods to make these very small nanoparticles? So back then, I need to say that chemistry was very strong and powerful. So chemical synthesis or wet chemical synthesis of inorganic nanoparticles is still the most dominant technology, because you can buy some chemicals, mix them together, and then try to synthesize nanoparticles to colloidal synthesis or impregnation. But Andreas always tried to investigate other technologies. So he has been working around with lasers, shooting high energy lasers on the surface to evaporate the material and then form nanoparticles in the gas phase as well. And he always came back to spark ablation because of the elegancy, the simplicity, just generating a simple spark between two solid rods, the material flexibility, because of the high temperature of the plasma, going up to 20,000 degrees Celsius. He could, let's say, be sparking platinum the 1 hour, and then the next hour he could switch to gold electrodes and then making gold nanoparticles. So after his whole scientific career, he was very convinced that using electrical sparks would be the best way to synthesize the most advanced nanoparticles in the gas phase, and give you the best source of a very high purity, high quality nanomaterial.
Yeah, this seems like an Occam's razor sort of situation where you have this, the simplest option ends up being the best. And in this case, it seems like this technology does a really good job of getting rid of a lot of the extras that usually have to come along with making nanoparticles. Usually you have to do a lot of solution chemistry. You have to do a lot of post-processing, and there's lots of issues then with also controlling the size and the effects of impurities. Right, as soon as you introduce a liquid, it's going to be really hard to ensure that's totally pure.
That's indeed one of the bases, is that controlling a gas environment is easier than controlling a liquid environment. And if you're synthesizing these nanoparticles in your liquid through those chemical methods, at some point you need to stop the growth. So you will add additional reagents to protect the particles to meet each other and grow to bigger spheres. And then most scientists, they always think that if they have the right nanoparticle size stabilized in their liquid, then their job is almost done. And they just need to pour the nanoparticle liquid solution on top of their sample, put it in the oven, evaporate the chemicals, and then by magic, the right size nanoparticles will end up onto their support or on their sample. But I can tell you, after speaking already in the last 10 years, so many PhDs, that this is you're not close to your final solution. It's like mission impossible to get those nanoparticles in their size, in their elemental composition, as they are directly onto your sample. Because the moment you heat up and evaporate the chemicals, you get all kinds of reducing reactions of the liquid solution. So you get contamination on your surface. If you go too high in the temperature, your particles will start to grow, agglomerate to bigger particles. So it's very difficult to get them out of the liquid solution onto your support.
And maybe as an aside, we could have a discussion about the importance of the size of nanoparticles, because that has a big influence on their properties. Yeah. These are effectively just clumps of atoms. This isn't bulk properties anymore. And at this sort of scale range, the addition or subtraction of one atom can actually have a pretty big impact on the performance of a given nanoparticle based on its reactivity or how it behaves when it encounters other electrons or other materials or light. So maybe you can talk a little bit about that.
Yeah, definitely. So I think in material science in general, the goal is always to tweak with the material properties and to make the materials better suited to do their job, store more energy, convert more photons into electrons, protect heat, or conduct electricity. Whatever your application is, that depends on the type of properties you want to optimize for. So at some sense, you need to have as many knobs to tweak the material properties. And one big possibility is to mix different elements. So if you mix all kinds of elements together, you can create all kinds of alloys. For example, the super alloys that you discussed in some of the previous episodes, that give you unique capabilities to create materials with slightly different properties. But the interest of nanoparticles is that they, besides the capability of mixing, they open up a completely new dimension to play with material properties. So this is coming from the quantum size effect. That means that if you make materials very small, so let's say below 5 nanometer in size, that you will get different physical laws to apply on the materials. And then you will go into a phase where the material is not longer defined by the properties that you see in bulk, but it becomes size dependent. So we also call them size dependent quantum enhanced properties. So if you take a 5 nanometer particle and you keep on making it smaller, then at some point there is this exponential shift in most of the physical properties of the material. So for example, gold becomes from gold to blue to red, and sometimes it's even transparent if it's small enough. Gold is very stable on the bulk side, so that's why we use it in jewelry. But if you make it below 5 nanometer, it becomes a super catalyst, and it starts to react with all kinds of chemical molecules. Gold is highly conductive, but if you make it small enough, at some point it's not conductive anymore. So you see that by controlling the size of these gold particles, you can tweak the physical properties of gold, and that gives you this completely new dimension to change the physical properties of your material. So if you start then making a microscopic material and you build it up out of these very small particles, and you have the right technology to make those particles of a specific size, then you can really create materials with different physical properties than the original material that you started.
Yeah, I mean, listeners might remember that it was just last year that the Nobel Prize in Chemistry went to the inventors of basically the quantum nanoparticles for these same reasons. So incredibly important and not totally fully understood or exploited technology. There's still lots of room for new techniques. So it's exciting to hear that not only is the field interesting, but now we're introducing a new mechanism whereby we can make these things. And like you said, we're going even further than that, because now you're saying, okay, it's not just about nanoparticles, it's about nanoporous films. So I'm curious, what additional things can you do when you go away from just nanoparticles and now you start to introduce nanoporous films? What technological advantage does that offer? What new opportunities does that give you?
Yeah, maybe also good to give the perspective on how we landed on the field of nanoporous films.
Yeah, absolutely.
So in the early days, the company VSParticle was really founded by the interest in nanoparticles, and we saw an almost exponential growth in nanoparticles being applied to a variety of different applications. And I think you can find almost any application where people are trying to incorporate nanoparticles to boost the performance of those materials and create better products. So that was also in the early days, a problem for us, because here we can't make a product or a tool, a piece of equipment that would fit all the different desires of those different scientists. But still, we went on, and in 2017, we introduced the first product, the VSP G1, which is basically a desktop system where you can put in solid rods of, let's say, gold. You can press a button, and then the system uses electrical sparks to break up the gold rods. And then out of the system comes a gas stream, either argon or nitrogen, filled with those gold nanoparticles that you have just evaporated. And we decided to put this system into the hands of scientists and give them the chance to tell us what would be the most important application fields, because we were not the experts in batteries and fuel cells and solar cells. So for us, with the limited knowledge, it was difficult to say, okay, we should fully focus the company to become successful in this specific market. So we used the research market, and we still do today, to really listen to them and see where they apply our technology to find the hotspots where we can scale our technology towards industrial applications and really move further. And this is also how we came to the field of nanoporous materials, because at some day we had researchers from DIFR, it's the Dutch Institute for Fundamental Energy Research, coming along. I think since the early days, we as a company has been very open. So we have done many, many collaborations in many different fields, and let's say high power LEDs to solar cells to quantum computers to any type of application to figure out where should we focus on. And this guy from DIFR, they came to us with a piece of plastic and they asked us, could you print a thin layer of iridium on top of the piece of plastic? And we, okay, iridium is in the right part of the periodic table. We can put it into the system. We have never sparked iridium before. So we coded it, we shipped it back, and not really knowing what the use case was. And then they, after a few months, they came back and they said, we were very impressed by the performance of your material. So they've tested all kinds of coatings themselves, but never get to the same performance as our initial attempt. And then we asked, okay, but what is then the use case for? And then they thought, okay, it's for PEM water electrolysis, to split water into hydrogen and oxygen, which was not an application we were focusing on. So then we started to deep more into this field. And then we also learned that next to, let's say, splitting water, electrolysis is also used more and more for converting CO2 into valuable chemicals. Right. And it could basically lead the chemistry industry into a completely new paradigm. So instead of using fossil fuel derived chemicals, you can start from CO2 and make all kinds of high valuable chemicals. And then we saw more and more need in the market of these thin film nanoporous layers. And when we moved into that field even more, we realized that in chip manufacturing today, you have beautiful technologies. They are very much advanced, thin film, solid layers, PVD, CVD, ALD. They are really mesmerizing. But they are all designed to make solid thin films because that is the foundation on which you produce computer chips. You make solid films and then you use lithography to make patterns into those films, and then you build layer by layer those chips. But at the same time, we are in this phase where we want to solve climate change and we want to, let's say, build a completely new energy infrastructure. And we have beautiful wind and solar farms, but we are still struggling to really store the huge amount of renewable energy in a day for a big city, for example. So large-scale energy storage is still a big problem that is unsolved. And if you look into those applications like next-generation batteries, next-generation electrolyzers for green hydrogen or for CO2 electrolysis, the performance of those applications are all determined by the performance of thin film nanoporous layers, basically the electrocatalyst in those applications. But there is no good technology to make thin film nanoporous layers. And that's how we figured out that by being the best already in making the smallest, purest nanoparticles, by just simply stacking those nanoparticles on top of each other, on top of a 2D substrate, we could make the most advanced thin film nanoporous layer in a very reproducible, very scalable manner. So that's how we started off the current focus on thin film nanoporous layers.
Gotcha. So that brings up a number of questions. How do you do any controls? I imagine, okay, so you're vaporizing small particle clusters off of your rods. Do you do any control steps before it actually enters the substrate to control the size, and how does that look? And then I guess a follow-up question, let's start with that.
Yeah, so we have two rods, and then past the rods, we blow a carrier gas, we call it. It's either argon or nitrogen. It's gases that you can get easily, and they are relatively inert. And the gas is coming in at room temperature. And when we form a spark, very locally on the rods, the temperature goes up from room temperature very quickly to 20,000 degrees Celsius or even higher, which results in this local evaporation of the material. And then when the plasma is dying down, you have this gas phase of the material with basically loose atoms. That's how you start. Loose atoms flying around, and then when the temperature goes down, the atoms start to hit each other and they start to stick. So we go from separate atoms to atomic clusters. We can make clusters of 2, 3, 4, 5 nanometers together, and these clusters, they keep on growing. But keep in mind that this cooling down plasma is being transported with a carrier gas at room temperature. So we have this fast cooling down of the plasma, back to room temperature. And in this process, you will see that those particles will start to stop growing around 2-3 nanometer in size. That's just the size where those materials are forming the first solid structure. So the melting temperature of those materials is for the first time coming above room temperature, you could say. So they are forming solid structures, and that freezes the primary particle size. So basically what comes out of our plasma are, in most cases, irrespective of the material that you use, primary particles of 2-3 nanometer in size, which are just the smallest stable particles that you can make on Earth at room conditions. It's impossible. If you make smaller particles, they will still collide and form and aggregate to form a bigger particle. So it's really the smallest, stablest particle that you can make on Earth. And what you still will have is that those particles will hit each other and then they will form agglomerates. So they will form open fractal structures in the gas phase if you let them longer in the gas phase. So this spark ablation process is very much a time-driven process. So the residence time that you give those particles in the gas phase is very important. If you give them a very short time, then you limit their growth potential. So then the particles will be as small as possible, or you will have as least as possible agglomerates. If you give them a lot of time, you will have much more agglomeration because the particles will then start hitting each other for structures. But the beauty is that out of this plasma, you will stabilize the material in the smallest, stablest particle that you can make on Earth. So there's no other technology on Earth that can make smaller, stable particles. The size of the particles is just determined by physics.
Gotcha. And then that can then be, I assume, a mechanism for controlling your nanopore size as well.
Yeah, so basically afterwards we transport the carrier gas into our printing nozzle, which is then printing into a printing chamber where we have an X by Z stage. And then at the nozzle, we are creating a pressure difference. In the chamber, it's a under pressure, a raw vacuum. Upstream, it's atmospheric because that's where the gas is coming from. And then we accelerate the gas flow to supersonic speed, basically to eliminate diffusion. You can imagine if you have a 2 nanometer particle flowing in a gas where the gas molecules are, let's say, 0.2, 0.3 nanometer in size, that the particles are bombarded from all directions. So they are flying into all different directions because of diffusion. And yeah, if we don't accelerate the particles to such a high velocity, they will never leave the gas stream. If you don't go to this high velocity, the particles will never hit the surface. They will just follow the gas stream and will never end on your surface. So we need to use impaction, the inertia of the particles at such a high velocity that they cannot follow the gas stream anymore. So they go into this straight trajectory while the gas molecules are being diverted to the sides. And that enables us to basically stack those nanoparticles on top of each other, forming a nanoporous layer.
That's rad. That's pretty cool.
And is there any post-processing, right? So there's no sort of adhesive. Do you do any like sintering afterwards to try to neck them together? I don't know if necking really makes sense at that scale.
No, so one beautiful part is that if you construct a nanoporous layer by building it from these almost single 2-3 nanometer particles, is that those particles have, because of their small size, a very strong van der Waals force. And because of this strong van der Waals force, they stick to anything. So we can print these nanoporous layers without a binder onto silicon wafers, onto GDEs, onto polymeric membranes, onto copper foils. It doesn't really matter. The van der Waals force always wins, so the material always sticks. And that is a fundamental problem in the current way we manufacture batteries, because we start with a powder, we have the copper foil, and we are trying to figure out how can we get the powder on the copper foil. But the powder has lost all its van der Waals force. So if you put the powder on the copper foil, it will just fall off. So what we now need to do in battery manufacture is to get this powder, put it into a slurry with all kinds of chemicals, binders, surfactants, and then slot-like coat that onto the copper foil, put it in the oven, dry it off, and then the glue in between the powder material will make it stick to the copper foil. So if you start with powders that don't have any intrinsic van der Waals force, you are stuck to this, let's say, ugly chemical slot-like coat process to make the powders or the porous material stuck to your support material. But if you build these nanoporous layers with the smallest particles that you can imagine, then you can leverage van der Waals force by itself without any additional chemicals to build stacking layers on all kinds of substrates. And the other part is because the particles are accelerated at supersonic speeds, is that the impaction energy that they have when they hit the particles before them will almost partially sinter them to the particles below them. So you will also get a very strong, on top of the van der Waals force, you will get an additional strength in your layer because of this partial sintering phenomena. And that's something you can play around with it by just changing the pressure difference, for example, upstream and downstream. So it's both. The technology by itself is material agnostic because of this high temperature in the plasma. And the other side is it's substrate agnostic. So it doesn't really matter. You can also print your material into microfluidic chips for very advanced material analysis or for more, let's say, biological type of systems.
I'm kind of curious. So we've done a lot of spray pyrolysis, which is, as you're describing this, it's kind of similar. I mean, the difference is that, right, you're essentially forming like a fog of your material from a liquid precursor, whereas what you're doing is you're evaporating it and then it's recondensing in the gas phase into these different particles, I guess. I'm curious, is yours then by definition, how high vacuum of a process is this and how scalable is it? Because one of the advantages, I know, and it's not an episode on spray pyrolysis, but because that's the technique that I know because we do it in my lab, one of the advantages there is that it's just done in air. I'm curious though, compared to things like PLD or other things that require high vacuum, where does yours land there, and what does that mean for scalability?
So the source, the process where we generate the sparks and we evaporate the material is all done at atmospheric conditions, atmospheric temperatures and pressures. In the printing chamber, to accelerate the gas flow, we pump down the printing chamber to a few millibar. So it's relatively okay. But keep in mind that let's say we are only using electrical sparks. So it's a purely electricity-driven process to convert any bulk material directly into the most advanced nanoporous material. And in a single step, fully automated process, you can get your nanoporous material printed as a nanoporous layer on any substrate.
Do you run into issues with, because locally where the spark is occurring, you say you go to 20,000 degrees or whatever it is, right?
Yeah.
What I've seen with other materials is that vapor pressure is typically an exponential. And so we know there's enough to volatilize it, but not all elements will have the same vapor pressure. And so is it a little bit tricky to get the right composition because you get differences in volatility? Does that make sense? Like if you want exactly a specific composition, how hard is it to get that dialed in? Or is there a lot of trial and error to get it sort of sorted?
That's a very good question. So there are different methods that you can apply. If you make a pre-alloyed electrode, so you have two rods of a, let's say, 80% gold, 20% silver composition, then multiple studies have shown that if you use that you will get nanoparticles of, let's say, almost exactly the same composition. So you can make pre-alloyed rods. So we've also been in contact with Cal Nano, also a sponsor of this program.
We love Cal Nano.
So then you can, with their spark plasma sintering, you can make all kinds of rods in any ratio of composition. And then if you spark it, you will get the same composition in the nanoparticles.
Cool.
But you could also do is if you have two different rods, especially if you have immiscible materials that don't form an alloy, normally, if you still use them both as a single rod and put them on opposite side of each other, then you will get ablation from both sides. So you will still create a plasma which is rich of atoms of both elements, and they will still be confined into very small nanoparticles that don't segregate into different materials. So you will get a 3 nanometer particle where still both materials are forming, let's say, small subgrains into the particle. So you will get a completely new type of material that you can never form in any bulk processing way because they don't alloy, they don't mix together. But in our process, you can still mix them into these very small particles that don't segregate.
That's super
cool. The other method, but the downside of this method is that you need to, let's say, if you want to screen a huge material space, you need to, let's say, create all those rods up front, which is a time-consuming process, and it's not something you want to do. Yeah. So in the past months, so last year we introduced our flagship product, the VSP P1, which is basically this full-fledged printer. So you just put in solid rods, you press a button, the system breaks the rods down to nanoparticles, directly prints them into any pattern that you want. We have full control over X, Y, Z. So you can make very complicated patterns. You can print gradients, whatever you want. But the printer is designed in a very modular way. So it cannot only accommodate a single source of nanoparticles, it can accommodate 2 sources. And then in one source, you can put silver. In the other one, you can put gold. And it's very easy to control the output of both sources. It's just a correlation between the current at which we charge the capacitors and the breakdown voltage, which is determining the energy per spark. So the higher current, you will have higher frequencies of sparks. Lower current, you will have lower frequencies of sparks. And more distance between the electrodes, the higher breakdown voltage, the more energy per spark. The closer the electrodes to each other, the lower the breakdown voltage, the lower the energy per spark. So it's a very easy knobs that you can turn to change the number of nanoparticles that you are producing per time. And then what we do is we combine the output of both generators into a single gas stream. So then you have a single gas stream where you have gold particles and silver particles flying around, and they are fed into the printer. So then we are printing a nanoporous layer that is made out of gold and silver nanoparticles.
But you can tune that ratio.
We can tune that ratio easily.
Cool.
We can make a simple script. We can print a 100 by 100 matrix where every dot is a slightly different elemental composition.
That's cool.
But then still you have a nanoporous layer with separated nanoparticles. But what we have seen in the past months is that if you heat that up to elevated temperatures, a few hundred degrees C, that you will see that the nanoparticles will form a new alloy without losing their porosity.
Yeah.
So you can not only change the elemental composition on the fly, but with this post-heat treatment, you can really form a new phase, a new material, a new alloy out of that composite material, and still have this nanoporous structure. And that is really something that excites me a lot, because that really means that you can screen through material spaces so quickly. And the beauty about the printer is that the standard system can use 2 sources. But we now have customers asking about 4 sources or 6 sources or 8 sources. So then you have a fully digital synthesis process that can make the smallest nanoparticles on Earth, form them in the most high powerful nanoporous layers, and can print elemental compositions in a huge space domain. And this is all, let's say, highly maybe we should talk about reproducibility in the inorganic space also a bit, because that is a very big problem that really annoys me a lot. But our goal is to get to superior reproducibility. And that's also now we see a lot of interest from top institutes that are trying to build what they call self-driving labs. That's also why we were at the AC conference.
That makes sense.
Because you need a digital-driven, fully automated technology to make superior nanoporous layers and screen a huge material domain. And that's really what our P1 is able to deliver for the first time in human history. Because before there was no technology to make high quality nanoporous layers. Let's stand alone that you can make a automated lab on top of it.
That's really cool. I wanted to go back to one thing you said a bit earlier, where you mentioned that elements that normally are immiscible can actually form coherent particles together. That's really interesting because it basically means you now have a size-dependent phase diagram where you have your bulk miscibility of these elements, and then you have the particle miscibility of them, which is kind of interesting because a lot of times there's compromises that have to be made, especially in catalysts, based on how well different elements will mix. But the ability to do that opens up a whole new space where now you're not you're bounded by different rules in terms of what particles and what sort of materials you can actually make, which is really astounding. And it really shows how much space you have to explore there and why that, automating that and getting to something that's not only reproducible, but fast and repeatable makes a lot of sense and is necessary to explore it.
That's also a bit the frustration we sometimes have in the company is because we need to be focused on bringing safe and easy to use products to the customers. But on the same time, we would also be interested as scientists to explore those material options. We know that if you process the material at reactive gases, hydrogen, you can make hydrides. If you process it with CO2, you can make carbides. We have been printing perovskites, nanoporous perovskites. But we can just only prove, let's say, initial studies that it can be done. And then we are sometimes jealous about our customers that can really run around in all the possible combinations. And for the first time can be quite quick in going through those different domains. But maybe let's come to the issue of reproducibility, because we have spoken to so many PhDs in inorganic nanoporous materials that started off their PhD with an interesting result from a former PhD in the same group.
Yeah, tell me about it, dude.
So many have wasted, or in the end ended up wasting 2 years of their PhD, not being able to get the same interesting result.
Just trying to reproduce it. And then after 2 years, they need to do something else to finish the PhD. We have spoken so many PhDs that were, the moment they realized that you could get a reproducible, easy to use, automated manner to make those nanoporous materials, that were almost crying at our booth and saying, okay, but then I could not make only 4 materials in my PhD, but I could really tested hundreds of them. And I think the irreproducibility of inorganic nanoporous material science is really holding back this enormous field. So if it's already impossible within the same group, what can you do among different groups? So what can the University of Toronto do with a great university here in the Netherlands? Almost nothing, because they both have their unique magic, their unique chemical recipe that they have developed over the years that was working somewhat. And you can't really, let's say, do the same. And I'm very positive to see that among some of the top PIs in Europe and the US, there is a strong interest to have the same high reproducible synthesis technology, so that you can really get this even distributed self-driving lab, so that you can make a same sample at different institutes at the same time. They can be processed at unique infrastructure. One is maybe very good in XAFs, the other one is good in high resolution TEM, and then you can get a complete picture of the same material without shipping around the samples to different institutes. And I really believe that in this new approach that we are trying to bring to the market, this gas phase synthesis and direct printing of those nanoporous layers can really be developed to very high reproducibility, much higher than you can get with the wet chemical processes.
So in addition to reproducibility, another issue that I'm aware of in the nanotechnology space is scalability. It's easy to demonstrate these properties on a benchtop, but it's really hard to scale that into a product. How does Spark Ablation fit into that? What is its potential for scalability?
Yes, and scalability is difficult because scale always comes at the loss of precision.
Yep.
So it's easy to make kilograms of material that are nano, but then you can't make a kilogram of material that all has 2-3 nanometers in nanoparticle size. So that's always the problem that you are facing. So we double down on Spark Ablation because, one, all the benefits that I already explained, the material agnostic, the fact that you are making the smallest particles without any chemicals, no contamination, it's a single-step process, and you can really make the best performing nanoporous layers. But more importantly is that it also offers a unique capability to scale up. So every Spark, you can see it as a batch process to make an X amount of nanoparticles. In our current on the market R&D systems, we go up to 300 sparks per second. Gives you milligrams of our production capacity. We are currently developing in-house what we call the G100, which is a completely different system that goes up to 20,000 sparks per second. So instead of doing 300 batch processes per second, we are doing a 20,000 batch processes per second. So then we are up to the 400 milligrams per hour production capacity, or at least that's the target where we are aiming. And then, so that is one axis. So increasing the number of sparks per second, increasing the energy per spark, that is one axis. And the other axis is just numbering up. It's not that difficult to just add more of those G100 sources to get to the kilogram per hour production capacity. And those two axes gives us a lot of flexibility to scale up. Yeah, and the fact that then you can enable with the P1, the current product, with multiple sources, you can enable the fastest, most powerful system to power self-driving labs, accelerating the development of those critical nanoporous materials. And then on the other side, we could translate overnight the recipes we have been printing on our R&D systems to our mass production systems really gives us a unique position to break down this 15-year timeline that we currently always face
for real.
to develop a new battery, to develop a new material. And our aim is to build such a powerful platform across all the different stages, and then try to bring it down to maybe 1 or 2 years. And that is really what we are aiming to achieve. But doing that also asks us to force and focus initially. So we are currently fully focused on creating this unique iridium layer for PEM water electrolysis, which is one of the biggest markets for nanoporous layers at the moment, growing very rapidly. And then we would like to expand to maybe next generation batteries or CO2 electrolysis or other very important energy related topics. But yeah, there are so many more type of materials that we can make. So we now focus on this nanoporous uniqueness, but if you heat the material up, you can make solid layers where you have well-defined grain sizes because you build the solid layer from well-defined grains. So we can also move into more solid type of materials later on by doing additional post-processing. So I really think that there's a lot of things we can still discover in the coming decades.
So Aaike, along with scalability is always the cost, right? Do you want to comment on how this thing compares to other sort of comparable technologies?
Yeah, maybe good to give the comparison between the state-of-the-art manufacturing process for nanoporous layers and our process. So state-of-the-art, you start with wet chemical synthesis of your nanoparticle in a liquid solution. You do the drying of the chemicals, you end up with your powder. You mix the powder with other chemicals to make your slurry, and then you do slot-like coating of the slurry onto your substrate, and then you go in the oven again to evaporate all the chemicals. So it's
a lot of processes.
It's a 7-step, chemistry-driven. Twice you are adding chemicals and twice you are removing chemicals just to make it happen. So every step has this irreproducibility. It's a difficult process to scale. Once you have it fully optimized and scaled, it's relatively okay, I would say. But if you want to change to a different recipe, it's a pain in the ass because if you want to go to bigger particles, first you need to optimize your wet chemical synthesis to get to the bigger particles. And then you need to know how does these bigger particles influence my viscosity in the slot-like coating process. So it's really, it sounds simple, but it's not. With our technology, we can basically eliminate 6 of those 7 production steps. We start with solid rods, you put them into our production system, you press a button, you don't need to become a scientist knowing how to make nanoparticles. You press a button, our machine breaks it up into these nanoparticles and directly prints in a fully automated, controllable process these thin film nanoporous layers onto your support without any chemical. There's no drying steps. You don't need to do any post-processing. So already keep in mind that I think Tesla had these very nice slides on their battery day that they showed if you can go to a dry coating process for batteries,
big deal.
You save 10 times the floor space, 10 times the energy because you don't need to do the drying and the recovery of your solvents. So we are currently making detailed total cost of ownership calculations with some of the biggest industrial manufacturers in the PEM water electrolysis business. And we really see very strong numbers coming up. And we really see that even though it's a brand new technology, which is always more expensive if you scale it up, that we can be very cost competitive to, let's say, very low-tech slot-like coating type of technologies. And most importantly is that those companies that are doing slot-like coating on large scale, they are very dependent on their suppliers of the nanoparticle powder. But in our system, you can make your own, let's say, type of powder on the fly that is unique to your product or your application. While companies, especially like Johnson and Matthey, they've been building in the past decades this unique experience in doing nanoparticle synthesis at scale. And if you acquire our system, you don't need that knowledge. You just get it for free into the system. You only need to know how to press a button.
Okay, Aaike, this has been a really fun episode. I think there are listeners who do nothing about spark ablation now kind of understand the technique, what it can and can't do, how it compares to other things. But this really is just introductory, and we know there's going to be a lot more. Do you want to say anything that you guys have coming down the line in terms of applications, what you're using this technique for?
Yeah, I think everybody sees the power of AI coming up. And I think the AlphaFold model, where they trained a very powerful AI model on a large experimental data set, has been proving us that that is the best way forward in material science. We can stop doing more science and really start to understand the more fundamental mechanism and basically crack the code. The same we want to do also in the inorganic space. Companies like Meta has already been very promising in building the AlphaVolt version for electrocatalyst. And the very thing that makes me excited is that with our technology, we now for the first time can really crank up the speed in building these large-scale experimental data sets. So I'm very positive to come back to this episode quite quickly to talk more about the work that we are doing in that direction and to really show the power of the technology in enabling these very advanced AI predicting models to predict the best electrocatalyst.
So listeners, stay tuned. Very soon we'll have a cool follow-up on this. Okay, as always, this episode is brought to you by the good folks at Elsevier and Materials Today. We think that they are an awesome publisher. They are increasingly a place where I want to publish some of my work. It is a high impact, great journal. Good stuff gets published there. So we hope that you will check them out. And we're grateful for them for supporting this podcast. We couldn't do it without them. So thank you, Elsevier and Materials Today. So obviously today's episode is brought to you by VSParticle. And you've heard all about the great things that they have. So I'm not going to belabor it. I'll just say that, look, I saw them talk at the Accelerate Consortium meeting, and I knew right away that this was a great company. They were doing top shelf science. And you've seen why by listening to today's episode. So thank you, VSParticle, for sponsoring today's episode.
And thank you, as always, for listening to this episode of the Materialism Podcast. If you have questions or feedback, please send us emails at materialism.podcast@gmail.com. Make sure to subscribe to the show on iTunes, Spotify, Google Play, which I think is YouTube now, or wherever you find your podcasts. And if you like the show and you want to help us reach more people, consider leaving a review. It helps us improve by letting us know what we can work on, and it exposes the show to new people. Finally, you can check out our Instagram page at materialism.podcast and see all the cool art that we make for the show, and connect with us to let us know what new material you'd like to hear about next. Finally, we'd like to give a shout out to Alphabot and Kolobyte for the music for the podcast. They both make a ton of really cool synthwave music, so go check them out on Spotify and YouTube. Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.